All right. So last time we talked about the quadratic formula. And just for a review, someone tell me what's the quadratic formula from memory? X is equal to, so I think I heard bits and pieces that were all correct individually. I believe somewhere along the way, someone did say the correct formula for the quadratic formula. So as a review, remember the quadratic formula is x is equal to negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. So that's what we did last time. And for the start of the lecture, we're going to veer away slightly from the quadratic formula. We will revisit it. I don't think we'll get to it today, but we'll probably get to it on Wednesday. So what we're going to be covering for today is a new type of number system. So before, we've already introduced a couple of numbers. We've talked about what a natural number is, what an integer is, what a real number is, and what's a rational number, what's irrational, and all of that. So the one number that we haven't talked about yet is the complex numbers. So I believe this is 1.3, if we're following through complex numbers. So we're going to introduce what is a complex number, how is it different from a real number, how is it similar to a real number. So to start us off for today, let's go ahead and do the definition of what I'm going to call the imaginary unit. So definition. We're going to have two definitions for this section. So the imaginary unit. Imaginary unit is the number where I squared is equal to -1, or equivalently, I is equal to the square root of -1. This is what we call it, the imaginary unit. And let me pull up my notes while I'm at it so I make sure I follow the same examples. So this is what we call the imaginary unit. It is the number I such that I squared is equal to -1, or you can say the same thing, I is equal to the square root of -1. So we know normally I can't do the square root of a negative number. If you try putting square root of -1 into your calculator, it's going to say something like error or domain error. It's not going to let you do it. So mathematicians said, essentially, why not? Why can't I do this? Well, usually we'd say square root of 9. We know square root of 9 is 3 because 3 times 3 is 9. But then whenever I talk about -1, if I think about any real number, there's no real number where you can say that number times the same number gives you -1. Because we have our rules about positive and negatives, right? Usually, if I say a positive times a positive, it's still positive. A negative times a negative is also a positive. So mathematicians introduced this number I. I know it was a little bit weird to say the number I, but the number I is the square root of -1. This is the biggest thing to pull from this definition. I is the square root of -1. You can imagine, I used the word imagine already. I stands for imaginary. And I mentioned this before, I believe for this class as well. Even though it's called an imaginary number, that doesn't mean it has no use. There's a lot of things that you can use imaginary numbers for. For upper level math, it actually helps a lot for a lot of calculations, computations. If you're doing some advanced stuff in physics, for example, I believe there's some applications for quantum computing and all that other fancy stuff. But for our class, we're mainly going to talk about how do I work with the imaginary number. So the imaginary unit is the number I, where I is equal to the square root of -1. This opens up a lot of options for us because now I'm allowed to do the square root of pretty much any number. Before we can do the square root of a positive number. It might have been an ugly number, but we were able to do it. But now we can do the square root of negative numbers as well. All right, so that's the imaginary unit. Now for the next definition, let me just move this up. We're going to introduce what is a complex number. So definition number 2. So a complex number is a number, not a big surprise, with the form a plus b times I, where a and b are real numbers. Remember this little notation here, this means a and b are real numbers. It's the shorthand for it. So we have a complex number. So it looks like an E, but it's technically like a lowercase epsilon, sort of. I'm saying sort of because mathematicians sort of edited it to be like that. If you see it typed, probably whenever it's being typed in a book, it looks a little bit more like that. So it looks like an E where you just erase the tip off of it, almost. So again, that just means A and B are real numbers. So a complex number is a number that has this form A plus BI, where A and B are real. So for example, if I did 3 minus 2I, that is a complex number. It matches a number plus or minus a number times I. And actually, whenever we're talking about complex numbers, one thing that you'll hear me say a lot is what's the real part of my complex number and then the imaginary part of my complex number. So in this example, 3 minus 2I, if I said, give me the real part of this complex number, what would you guess it probably is? 3. It's a number that we recognize as real. But what's the imaginary part? Yeah, so as it turns out, we'll call the imaginary part, in this example, is -2, the part with the I. So real part is the number by itself. In this case, 3. The imaginary part is the part that has the I on it, so -2. So I have a real number plus the imaginary part times I, giving us a complex number. So we've gone ahead and defined complex numbers. I'll give y'all a moment to copy this down as needed. So again, while y'all are writing, just some off-topic things about complex numbers. For most of this class, besides probably a couple of these lectures that we'll be covering for today and probably this week, most of the time we're only dealing with real numbers. But for today's lecture and this week, we're also including the complex numbers, the imaginary numbers. But after this week, for the most part, we'll just say we only care about the real numbers. Like I said, there's a lot of things you can do with complex numbers. There's a whole field of math dedicated to talking about these imaginary or complex numbers called complex analysis. All right, so we've defined what a complex number is. So now I'm going to go ahead and introduce this one rule from algebra that a lot of people tend to forget, and it involves a square root. Does anyone still need some time to copy this down before I move on? All right. So let's recall this rule. If A and B are not both negative. So if I have two numbers where they're not both negative, it's okay if one of them's negative, but I want to make sure both of them, that I don't have that both of them are negative. Then I can say the square root of A times B is equal to the square root of A times the square root of B. In other words, as long as both of them aren't negative, I'm allowed to split apart my square root. And I'm going to repeat myself again. It's okay if one of them is negative. I just want to make sure that both of them are, that not both of them are negative. So as long as I have two numbers, either both positive or at least one of them being positive, I'm allowed to split up a square root. And actually, you can do this for any radical also, like a fourth root, sixth root, stuff like that. But really, we like working with square roots usually. So if I'm looking at some quick scratch work examples, if I did the square root of 32, for example. Well, one thing that I think I can say is 32 is the same thing as 16 times 2, right? So that means I can still write this here times 16 times 2. Well, by my rule that I've had here, I'm allowed to split apart my square root and write this as the square root of 16 times the square root of 2. Why is that useful for me to write it that way? How can I clean that up? Well, they're a placeholder for a number. Yeah, that's also something really useful that we'll be able to do. That wasn't the answer I was expecting, but that is a good point that we'll see next week for whenever we do square root of an x. But the other reason is that here, I know what the square root of 16 is, right? That's a clean square root. That's 4 square roots of 2. In other words, by doing this, it gives me sort of a more natural way on how do I clean up a square root. 32 is not a perfect square root, but I can break it down to something that does have a perfect square root, like 16. I can't always do that, but when I can, it's really nice. All right, so this was a quick example. What if I did something like this? What if I had the square root of, let's do, I don't know, negative 27, something like this. First off, there's a negative under there. We'll talk about that in just a moment. So what might be a convenient way to split up 27? Yeah. So 27, in my head, I'm thinking we can do, say, 9 and 3. but it's a negative 27. So I can take it a step further, and I can do, let's say, negative 3 times 9. Negative 3 times 9, yeah, that's negative 27. So clearly, if I look at negative 3 and positive 9, they're not both negative. So by my rule, I'm allowed to split it up. So I can write this as the square root of negative 3 times square root of 9. Well, square root of 9, I know how to clean that up. Square root of 9, that's 3. But now, how am I going to deal with the square root of negative 3? Is there anything I can do there? So there is going to be an I in there. And just for notes, I'm going to show you where this I can come from. Would y'all agree that negative 3, that's definitely negative 1 times 3? They're not both negative, so I can split it apart. So I have 3 times square root of negative 1 times square root of 3. All right, so 3, that's already a clean number. Square root of 3, there's not really anything I can do there. But what can I do with the square root of negative 1? It's I. Remember at the beginning, I said the square root of negative 1 is I. So I get 3 times the square root of 3. And then the I comes from the square root of negative 1. And usually the standard is like, we like putting I at the very end. One other thing I want you to be careful about is that I is outside the square root. It is not underneath the square root. It is outside, which is why usually whenever I write my square root, I put a little bit of an edge at the very end to say it closes right there. So whenever we start doing examples, you're going to start seeing I'm not going to bother writing negative 27 is negative 3 times 9 and so on and so on. We're actually going to start doing this a little bit quicker. All right, so now that we have some introduction to it, let's go ahead and do an example. Example 1, simplify. So I have 3 parts for this example. Let's start off with square root of negative 9. So for the notes and lecture, I'm going to do this a long way, but you're going to see that we can do this really quickly if we really wanted to. All right, so negative 9, I can split that up into, well, 9 times negative 1. So negative 1 times 9. Or you can write 9 times negative 1, doesn't really matter. Which I can split up to negative 1, the square root of negative 1 times square root of 9. There's other ways that you could have done it, but the reason is that I already know that 9 is a perfect square root. Because if I did a square root of 3 times 3, I can't really do much there. So in other words, I'm just trying to find the perfect square root in there. So that's why before, like, I chose 16, because I know square root of 16 is perfect. All right, so square root of 9, what's that? 3. Square root of 9 is 3. What's the square root of negative 1? I. We're done. So why did I say that really we're probably going to start doing this a lot quicker? Well, in the beginning, square root of a negative number, that's a big red flag saying your final answer has an I in it. So if you see square root of a negative, you can go ahead and say, my final answer has an I. If you want, you can go ahead and write that down. So the I deals with the negative. After that, I'm just asking what's the square root of 9? We get 3. So we have 3I. All right, so we're done with part A. So anytime, the way I'll word this is that right here, by definition, I is the square root of negative 1. But you can also say square root of a negative, there's going to be an I there no matter what. So whichever explanation, you get to the same point. All right, so let's go ahead and do part B. Let's do the square root of, let's do something that's not a perfect square root. Negative 18. So take a moment, see if you can do this one. Start off by saying, is there a way I can break up 18 to make it into a perfect square root and something else? So how can you make 18 partially into a perfect square root? That's one way we can think of this. I'll give you all a minute to figure this one out. So what's one way that I might want to break 18, negative 18 down? So I'm hearing different answers. So we're going to do it both ways just to show y'all that really it's the same thing one way or another. So one way you can break down negative 18 is, well, negative 2 and 9, right? And if you do it this way, you get square root of negative 2 times square root of 9. Yes. Yeah, so what I'm going to do is, let's do this one. I'm going to show you why it's going to actually be the same thing. So what's square root of 9? Can I break down 2 anymore? No. But since it's a negative 2, I can put out an I and write this as square root of 2I. So good question on why did I not put it on the negative, put the negative on the 9? Well, I can. It just means I do this. 2 times negative 9. I can split this up into square root of 2 times square root of negative 9. Square root of 2, we couldn't do anything, right? That was already alone. What's the square root of 9? 3. But because it's a negative 9, I have to put the I on there. So again, for this one, square root of 9 is 3. But because it's a negative 9, we put an I there. So that's why it doesn't really matter which one you put it, as long as you get that I at the very end. Or you could have said this, square root of negative 18, square root of a negative number. I know that this is the square root of 18 times I, and then I clean up the square root of 18 from there. So really, it doesn't matter as long as you end up with that I at some point. The last thing I want to mention about this one is for people who gave me 6 times 3. So, for example, I could say that this was 6 times 3, negative 6 times 3, or 6 times negative 3, doesn't really matter. Well, I can break down 6 if I want, right? Because 6 and 3, these are not perfect square roots. So this is another method to clean up a square root. I could say that this is, for example, negative 2 times 3 times 3. Well, remember what a square root does. A square root is looking for pairs. So do I have a pair underneath the square root? I got a pair of 3s. So what a square root does is it takes a pair and moves them into 1 on the outside. So this becomes 3 times square root of negative 2. But we know how to do square root of a negative. That just means I throw an I on the outside. giving you 3 square roots of 2, and on the outside, an I. So all these are still essentially the same method, just written out in a different way. Reminding y'all, for any time we get to exam time, I'm not looking for one method over the other. As long as you're getting the 3 square roots of 2i using legit math, then it's fine. An example of something that would not be legitimate math is if you said square root of negative 18. This is an example, a real example that I had one time. Someone said square root of negative 18. This is equal to something like 36 over 2, and then they said 3 square roots of 2i. They wrote something like this, and that makes no sense. Like, how'd you even get there? In other words, whenever we start getting to the test, what I want you to do is give me something that I can follow. Don't give me something where it's like, well, I know the answer because I know how to do it. I know you know how to do it, but I need you to show me your work, more or less. Like, this doesn't help me at all. How'd you even do that? Is it technically more or less correct? I guess. Another example is something that wouldn't be legitimate math. Someone on their test, I said, how'd you get the answer? He's like, well, my phone told me. That's not a good way. Well, first off, you told me that you cheated, first off. And also, that's not even a good way for me. All right, so this was our example 1, part A and B. Let's do a part C. What if we throw this in? Negative square root of negative 17. I'll work through this one with y'all. This one's actually a lot simpler than what you may be thinking looking at it. So in the front, there's a negative, right? So I'm just going to leave that alone for now. So in front of the square root, there's a negative. That's a given. We're taking the square root of a negative number, so I know my final answer has an I in there. I'm going to go ahead and just write that I ahead of time. So far, I've got this. I'm able to take out the negative essentially by putting an I on the outside. But looking at 17, can I even break down 17? No, 17 is prime. The only way to make 17 is 17 times 1, and that's not going to do anything for me. We're done. This was an example saying you can't always break it down. Sometimes the answer is the most obvious one, what we have already. So we don't always need to break it down. If we can, we should. But in this case, 17, there's no other way to make 17 besides 17 and 1, which doesn't help us. All right, so we're done with part C. A very quick one just to show you that we can do square root of any number now. All right, so we just introduced our complex numbers, that is our imaginary numbers. Well, whenever you first got introduced to regular numbers, 1, 2, 3, 4, the first thing you probably learned or should have learned is how do you add, subtract, multiply, and divide them. We just introduced a new type of number. So we're going to learn, how do I add imaginary numbers? How do I subtract them? How do I multiply and divide them? So the good news is that for adding and subtracting, there's not really going to be any big difference. Multiplication and division, we will have to put a little bit of extra effort. So I'm going to go ahead and write out the formal definition on how do I add and subtract them. I'll take a moment and say, don't get too caught up in this definition or equation. It's me writing it very formally. So operations. First, we have addition and subtraction. So let's say I have two complex numbers. Let's say it's a plus bi. That's a complex number. A and B are is some real number. And then I want to add or subtract. If I'm adding, I'm just caring about addition. If it's subtracting, I care about subtraction. Let's say another complex number. C plus DI. This says another complex number. Then this is going to be equal to A plus C. Oh, plus or minus C, sorry. Plus B plus or minus DI. First off, I want to emphasize, do not get caught up in, oh, what's A, B, C, and D. I'm going to talk about what does this mean. This is just a formal, very general way of writing it. So actually, what I've written here is, if you want to add two complex numbers, all you're doing is saying the real part plus or minus the other real part. That's what's happening over here, real plus real. The imaginary part plus the other imaginary part. That's why we have B plus or minus D here. So again, this is looking a lot more complicated than it actually is, but we just need it for formality and writing out all the theory stuff. So we have our first operation, addition and or subtraction. Obviously, if it's minus in the middle, then it should be minus on the right side also. So let's go ahead and do an example with this. Example 2, same instructions, simplify. Part A. What if I have 3 minus I plus 5 minus I? So this is one complex number plus another complex number. So the way I usually do this is that let's do the real part and then let's do the imaginary part. So what's the real part of my first number? It's 3, right? What's the real part of the second number? All I'm asking is what's 3 plus 5? We get 3 plus 5, 8. That's the real part of my final answer. Now, what about the imaginary part? We have negative I plus negative I, which is what? Negative 2i, because it's negative 1i plus negative 1i. We're done. Again, you can see how this is just me saying the first number plus the first number, imaginary plus the imaginary. So we have 8 minus 2i as our final answer. Let's do a part B. This time, let's add some subtraction in there. And move this up here. See if I can erase this. So part B, let's go ahead and do 3i minus 2. B, 3i minus 2 minus I minus 5. What are a couple of things you're noticing is a little bit different in part B than what I did in part A? Does anything look a little bit different? Yeah, that's what I'm noticing too. There's I's in the front. Does that really change anything for me? I'm still just doing the real part minus the real part, imaginary minus the imaginary part. So let's start off with the real portion. What is the real part of my final answer? Yeah, so if I want the real part of my final answer, here we have negative 2 minus negative 5. So what's negative 2 minus negative 5? Yeah, so this is a side note. You don't have to write this. -2 minus -5. So minus a negative becomes a plus. So this is why I include the negative. Make sure that you're keeping track on, is it minus a negative or is it minus a positive? So what's -2 plus 5? 3. So the real part of my answer is 3. Again, especially if you ever see a minus, be extra careful about where all of your signs are going. This is -2 minus -5. Minus a negative becomes a positive. All right, what about the imaginary part? What is going to be the imaginary part of my final answer? Yeah, so imaginary part here is 3i minus I. So it's 3i minus I. Yeah, I get plus 2i. Again, I'm not going to make a big deal if you put 2i plus 3. 1 plus 2, same thing as 2 plus 1. Is that usually standard is that we put the imaginary number at the end. We're done. So here we did the real minus the real, and then the imaginary minus the imaginary. Let's do one more for addition and subtraction. So for part C, let's do I minus 2. Something like what I have here. Once again, I'm going to start off with what's the real part of my final answer and then what's the imaginary part. So to start us off, what is the real part of my final answer? What do you think it's going to be? I'm hearing a -2 and I'm hearing a +2. Which one should it be? Well, look at what we have here. We have minus a -2. What happens whenever we get a minus -2? It becomes a plus. So I know I've got a +2 here. Remember, this negative goes to both of these. What about my imaginary part? What's the imaginary part of my final answer? What do I get, if anything? Let's see, I got I minus I, 0. If I told you what 2 minus 2 was, you would say 0. I minus I, we get 0. So I'm not going to bother putting +0 on there. So my final answer actually has no I on there because it canceled out. So we've done some examples about adding and subtracting complex numbers. Any questions about how I did any of those steps so far before I move on? I'm actually going to go ahead and ask a particular question. So we had these 3 examples. For part A, my final answer was 8 minus 2i. Is that a complex number? Does that look like a plus or minus bi? Yeah, for sure. It's got the real and the imaginary part. Same thing for part B. That looks like a plus or minus bi. That's fine. So I think we can agree A and B, the final answers are complex numbers. But what about for part C? Is +2 a complex number? Are we sure? Complex numbers look like A plus bi. A plus or minus bi. Well, we'll say plus bi. Here I have 2. Clearly I have a real part, right? 2 is real. But I'm still allowed to write this if I wanted to. Is this still the same thing? It's still equal to 2. So in fact, 2 is still a complex number because in that definition, there are no rules about me saying B can't be 0. I just said A and B had to be a real number. And I'm pretty sure 0 is a real number, more or less. So this is saying that complex numbers are actually more broad than real numbers. So every real number is actually a complex number. So this is going to take me to a side note. So first off, can we agree that every real number is a complex number? Because I can do this basically. How many real numbers are there? Yeah, infinitely many. If we have an infinite number, how many complex numbers do I have? Infinitely many also, right? All right, which one is bigger, the real numbers or the complex numbers? The complex numbers, but y'all also said that they're both infinity. Something weird is happening, right? We just said that there's more. This is a complex number that's not real. So clearly there's a lot of examples of things that are complex but not real. But at the same time, there's an infinite number of real numbers and an infinite number of complex numbers. So I'm using this as an opportunity to introduce something I say a little bit for my calculus classes. This is the idea, very broadly speaking, of one infinity being bigger than another infinity. Because we clearly know that there are examples of complex numbers that aren't real. Even though they're both infinity, we have the concept of one infinity being larger than a different infinity. So depending on how you look at it and what type of rules you use, you might say they both have the same amount of real numbers. I mean, the same amount of numbers. Or you might say there's more complex numbers than real numbers. So that's whenever things start getting complicated, because whenever you start doing math with infinity, it starts breaking a lot of rules. Like for anyone here that is doing calculus, you'll learn about when do I get infinity over infinity being 0 and some weird stuff like that. Long story short, infinity makes us break a lot of rules that we usually know about math. But fortunately for our class, we're not really dealing with infinity that often. I might mention it every now and then, but for the most part, it tends to be a one-off thing for pre-cal algebra. All right, so the last thing I'll mention is that if you've noticed on Blackboard, I've posted the first homework assignment, homework set 1. There's one section, there's still part of this lecture that we haven't gotten to. We'll finish it on Wednesday. The first homework will be due on Sunday at 11:59 p.m. So Sunday night. It's 15 questions. Most of it is from what we did during the first week, and the rest is what we did today and Wednesday. The way it should work is that if you've already purchased your access code from the bookstore, or if they emailed it to you, it should be linked to your Blackboard already, and you should be able to just click on homework set 1. Yes. So let me see if you can go ahead and turn it around and show me what's going on there. It might be asking you to sign in or something like that. Oh, you're not connected. Yeah, the Wi-Fi goes on and off a lot. So go ahead to pre-cal algebra. See if you can click on homework set 1. Okay, so yeah, so click next on it. So it should open up and say open in a new window. It'll open a new window. If you've already got the access code through the bookstore, or if they emailed it to you, whichever way, it should be automatically linked to Blackboard. You just have to click on the link. It'll take you to homework 1. Ooh, that's not good. I'll have to take a look at it. In the worst case scenario, I'll just push back the homework a week until we get everyone fixed. I'm not going to penalize people for having technical difficulties to put that out there. It looks like there are a couple of people who are having some issues. I know I saw in the grade book that there are a couple of people that were able to get into it. I'll have to contact IT, see if they can get it all fixed through. But if you can access it, good. If you can't, you can always see me in my office, and then I can go right onto your computer, and then we can work on it. I did move into my office now. It's in Carter 214. So if you go to the third floor and then go through the corridor, I'm like on the left hallway. All right, but besides that, I'll see y'all on Wednesday.